This is section 16.7, part 3, and we're continuing to talk about doing work, this time by stretching and compressing springs. Once again, we're going to rely on a law of physics to help us out here. We know that in general, work is always force times distance. This time, because we're working with springs, we're going to rely on something called Hooke's law that says that force, F, required to compress or stretch a spring within its elastic limits, is proportional to the distance x that the spring gets either compressed or stretched. So F is proportional to, or equal to, a constant times x. That value of K, that spring constant, depends on the specific nature of the spring. Really, it's how stiff or loose that spring is that determines that K value. A few important concepts for us. First of all, a spring is in equilibrium when it's neither compressed nor stretched. So equilibrium is just the natural length of the spring. In any diagrams that we draw, I will always consider equilibrium to be represented by x equals 0. A spring can be stretched by pulling on the spring or applying a weight. Either the pull or the weight itself could be the force. So if we stretch our spring, in other words, go beyond the equilibrium position, here was x equals 0, the natural length, and here's going to be an x that's greater than 0. We considered the stretch to be a positive x value. If we compress our spring by pushing with some force F on it, the spring, of course, gets shorter then. And so if x equals 0 still represents the natural length, this x value would be negative. So a stretch is a positive x value, a compression is a negative x value. All right, let's take a look at calculating the work done when we stretch or compress a spring. In our first example, we're going to suppose that a force of 10 newtons is required to stretch a spring 0.1 meters from its equilibrium position, original length, and hold it in that position. Assuming that the spring obeys Hooke's law, first of all, let's find the spring constant, K. So we know F is equal to Kx. In this case, we were told that when the force is 10 newtons, the stretch is 0.1 meters. And by the way, I'll make a mention here. You're going to want to make sure that you're in our standard unit systems. Right here, we're entirely in the international system. Newtons and meters is fine. But I don't want to mix things. I want to make sure that I'm in those standard either American units, international units, or CGS units. So in this case, the K value, 10 divided by 0.1 would be 100. The units are actually newtons divided by meters, and that works out just fine when we plug everything in the long run. So I'll notice then that I could write my force equation, Kx, as 100 newtons divided by meters, times x meters. The meters would cancel, and I'll get 100x newtons for my force in this case. So the units of force turn out to be newtons. All is well with the world. All right, next question. How much work is needed to compress the spring 0.5 meters from its equilibrium position? So here's the thing about stretching and compressing. We're really working with a variable force. Let's think for a moment about why that is. If I imagine my spring in its equilibrium position, no stretch or compression yet. And I begin to stretch the spring a little bit. Just from experience, you know, right? At first, the spring isn't that hard to stretch, but you have to do more work the further you stretch it. It gets harder and harder to stretch. So the force required is variable, depending on where exactly we are in the X value, the amount of stretch, right? If I stretch it a little bit, I would have to use less force. If I stretch it a whole bunch, I would have to use more force. So because it's a variable force, that tells me that I'm going to have to integrate to find the work. I can't just do it algebraically, right? Constant forces, we can find work algebraically. Variable forces, we need calculus. So let's go ahead and integrate. We know our force, because we just calculated it, was 100x newtons, but I won't put the units in the integral. And for the distance, each value of the force only applies to a tiny little piece of distance, and then the force changes and becomes something else. So I'm just going to use dx, or the representation of delta x, as the distance that I can move under any particular value of the force. Now in this case, the limits of integration are right in the problem. We want to compress the spring, 0.5 meters, so that would be an x value of negative 0.5. That's where we want to end up, from its equilibrium position. Equilibrium is always x equals 0. That's where we want to start. So we'll always integrate from start to end. So I'm going to go from 0 to negative 0.5. And as usual, again, these are very easy integrals to do. I'm just not going to take the time to do them on the video. If you want to do them by hand later, feel free, but I'm just going to use the calculator just for speed. So getting that one done, I punched it in and I got 12.5. And in this case, my units are newtons and meters. So this would be Newton meters. This is in general how we're always going to solve these spring stretching and compressing problems. We'll always integrate our force function, dx, that's our distance piece, so we'll have force times distance. And then we just have to figure out the limits of integration by thinking about the starting and ending positions of our spring. Let's do a couple more. How much work is needed to stretch the spring? 0.25 meters from equilibrium. So it's the same spring, so my force is still 100x. I'm still going to represent the distance as dx. And the only thing that's changed are my limits of integration. This time I want to stretch the spring, 0.25 meters from equilibrium. So since I'm stretching, that means I'm going to end up at a positive 0.25 for x. And once again, I'm starting at equilibrium, so I'm starting at x equals 0. So that gives me the limits of integration on my integral. And when I punched that one into the calculator, I got 3.125. Still Newton meters. Now notice that we stretched one, compressed on the other, but we still get positive values of work in both cases. That seems normal. In both of these problems, we started from equilibrium, but we actually compressed more than we stretched. We compressed by 0.5 meter. We only stretched by 1/4 meter. So we had to do more work here than we did here. All right, part D. How much additional work is required to stretch the spring 0.25 meters if it's already been stretched 0.1 meters from its equilibrium position? So the spring still hasn't changed, meaning my force is still 100x. My distance is still dx. This time, I'm trying to stretch the spring 0.25, given that it's already been stretched 0.1 from equilibrium. So what does that really mean for me? I'm going to draw myself a little diagram here. At the beginning of this problem, we were already at x equals 0.1, right? That's where we're going to start. Now I'm going to stretch an additional 0.25 meters. So that means I'm going to end at an x equals 0.35. So there are my limits of integration for this problem. And when I plug that one in, I got 5.625 Newton meters. Okay. One additional thing to point out to you before we leave this problem. Notice that I stretched the spring 0.25 meters here, and I also stretched the spring 0.25 meters here, but I got different answers. This goes along again with what we know, right? This was the first 0.25 meters. I was starting this time at x equals 0 when I stretched to the 0.25. The first 0.25 meters is the easiest to stretch, so I did less work. Here, I had already stretched the spring some, so I had to put in additional effort or additional work. I got a bigger value for work here when I stretched it out further. All right, a couple more examples of spring problems. In this one, we have a force of 40 newtons required to hold a spring that's been stretched from its natural length of 10 centimeters to a length of 15 centimeters. How much work is done in stretching the spring from 15 to 18 centimeters? All right, there's a few different things that occur to me here. First of all, I'm going to notice that I do have a little bit of a problem with my units. Looks like I want international since I have newtons, but I would really rather work with Newton meters, Newton centimeters. It's not that it's not a okay unit, it's just not standard. So I'm going to start here by converting everything into meters. Dividing by 100, I'm going to say that 10 centimeters is really 0.1 meters, and the 15 would be 0.15 meters, and 18 would be 0.18 meters. So let's start just by doing those conversions so we've got standard units. All right, first of all, I need to find my force equation. We know F equals kx, Hooke's law, and I was told that 40 newtons will stretch my spring from its natural length, 0.1 meter, to a length of 0.15 meters. Now let's think about that for just a moment. The natural length, the 0.1 meters, is always defined as x equals 0. So in this case, even though I was given the length of the spring, 0.1 meter, it doesn't matter. I'm still going to call that starting position x equals 0. When I get out here to 1.5, or 0.15 rather, I've only stretched it 0.05 meters. So always start with the natural length of the spring being your x equals 0. That's what I'm going to plug in here. The 40 newtons equals k times that stretch of 0.05 meters. Dividing, I get 800. And again, units would be newtons over meters. So my force equation is actually F equals kx, F equals 800x. All right, now I'm ready to find the work. I now know that my goal is to stretch from 0.15 to 0.18. So if I go out a little bit further here to 0.18, let's see, that was the x equals 0.05. This would be 0.08 past equilibrium. So this x is 0.08. This is my starting position. This is my ending position. Again, everything's relative to the natural length of the spring, which we define as x equals 0. So I'm integrating my force equation, 800x, times the distance, which we're using dx, a little piece of distance. And in this case, we're integrating from 0.05 to 0.08. Again, just plugging that into a calculator, I ended up with 1.56 Newton meters. All right, one more. A force of 750 pounds compresses a spring 3 inches from its natural length of 15 inches. Find the work done in compressing the spring an additional 3 inches. All right, in this case, they actually told me how much it was stretched or compressed. It didn't tell me the actual length of the springs. So I don't really even need this information. It's extra. It's true, but I don't really care about it. What I know is a 3-inch compression from equilibrium, and then an additional 3-inch compression from there. All right, let's start once again by thinking about our units, and then we'll find our force equation. Once again, I've got a little bit of inconsistencies, not terrible. Since I have my force is 750 pounds, I'm in the US system, meaning I'd really like foot pounds. So let's go ahead and say, instead of those 3 inches, let's think of that as a quarter of a foot, 0.25 feet. And I'll start with finding my force equation. Always Hooke's law for spring problems, F equals kx. The force was 750 pounds, and that was a compression of 0.25 feet. And by the way, k is always considered to be a positive constant. Technically speaking, I probably should be using an absolute value of x here when there's a compression, when I find the k value. I don't really even want to do that. Let's just say that k is always going to be the absolute value. And that was what, feet? So when I divide this time, I get 3,000 for k. And that would be pounds over feet. And I'll just make that note. K always positive. Okay, that means my force equation is going to be 3,000x. And I'm ready to find the work. So let's see here. If I imagine what's going on in this problem, if this is x equals 0, the equilibrium position, we were told what happened when we compressed the spring a quarter of a foot. So that would be an x value of negative 0.25. And then we're going to compress it an additional quarter of a foot, and we want the work required to compress an additional quarter of a foot. So I probably should have put this down here. This is our starting position. And then to go back another quarter of a foot, would give us an ending position of negative 0.5. And again, it was that word, an additional 3 inches or quarter of a foot. So from the first quarter foot, how much extra work to go back another quarter of a foot. So I integrate my force function, 3000x, times distance dx, work always force times distance, and my starting position, negative 0.25, to my ending position, negative 0.5. And I ended up with 281.25. And that would be foot-pounds. All right, that brings us to the end of the spring problems. So I'm going to stop there and do one last video for the fluid pressure problems to finish out this section.